Wonderful, thank you for the introduction. Okay, so the topic for this presentation is fairness in natural language processing. To kick off, let me give some exemplars of what it is I mean when I talk about fairness or unfair AI. So I'll start out with some non-NLP examples, all very recent examples. So the first one is the Twitter image cropping algorithm, where there's been a lot of discussion about bias in terms of when you have a larger image that it crops down in terms of your Twitter feed, and there are multiple individuals in a given image. Is it biased towards selecting individuals of particular skin colors over others? And there was recently a bounty that was offered by Twitter itself, which was very impressive, where they asked researchers to look into this, and the bounty was reward to the person who dug the deepest in terms of revealing the bias. And it's possibly too small here to read, but observed that it was biased towards younger, fairer skinned, more effeminate, sort of warmer toned faces. So, sort of very biased towards very particular demographics. Another example from the US relates to mortgage approvals, where it was shown again very recently in the last couple of weeks, very systematically in terms of some of the methods that are used commonly across institutions that offer mortgages for home loans, for example, that given exactly the same credit score, key demographic variables such as race and gender really had an impact on the likelihood of an individual being awarded a mortgage or not, or having it approved or not. One from NLP, which is very close to home to me because it relates to a system that I've published, which is in very wide use around the world, is in the context of language identification. So given a document, what language is it predominantly written in? Is it English? Is it Swahili? Is it Hindi, say? And the particular analysis that was done by researchers at Stanford was to look within different varieties of English at the ability of different language identification systems, with the blue line at the bottom here being our langid.py. How well are they able to discriminate varieties from different countries, and how does that correlate with the human development index of the country? So basically the sort of wealth factors of those countries. And very confrontingly, what they found was within English, for US English or Australian English, say, it was very reliable. For Nigerian English or even Indian English, it was much less reliable. So you had this very strong correlation between the wealth of the country that particular variety of English was spoken in and the ability of our system to discriminate it. So basically there are systematic biases towards particular demographics. So there's no question that there are issues in deployed AI systems. What do we do about this is the topic of today's talk. So in the NLP context, it's worth starting out and recognizing that people tend to talk about two primary variables in terms of fairness. So the first is source fairness, as in the source author who has written a particular document. So I've got an example here, an excerpt from a movie review. You can see the link at the bottom of the page and pick up on the fact that it's for The Princess Bride. And if you read this, it's an adventure, devil may care world of Douglas Fairbanks, etc., etc. You can probably get a sense of the background, the age, the perhaps country of origin, the gender, possibly as well, of this individual, and possibly unsurprised to hear that this was written by a male 50-something-year-old at the time, white, Brit. You maybe couldn't quite work out all of those variables, but we know there's a lot of demographic signal, a lot of sociolinguistic signal in terms of the style of writing. So this relates to source in terms of our models picking up on these different stylistic and peculiarities in exactly how we express ourselves in the same language, leading to disparities across some of these different protected attributes. So the counterpoint to that is target or reference bias.
I'm very sorry for the I'm very
yes.
sorry for the interrupting, but the attendees are mentioning that they see only the main screen as the first slide, but they don't see if you're switching, just in case if you're switching.
Yeah, no, I am switching. That's odd because I see on showing main screen that it's transitioning. Should I?
Yeah, let me make myself as a presenter, and then I give you back the opportunity to present. Maybe there was some technical glitch. 1 second.
Yes.
Yes, feel free to try now.
Okay. So when I look in my interface, it says showing main screen and a slide. So what is fairness? Do you see that?
Yeah, it seems that it was frozen once it was actually transmitted for some reason.
Okay. So it's now fixed.
We don't see now your screen still. Maybe. Are you sharing?
I should be. Let me stop sharing and start it again.
Sure.
So you should now see a slide titled Training Models to be Fairer, Take 1.
No, not yet.
Okay, so what do you see?
Nothing. It shows that you're not presenting.
Huh. How odd. Let me try this. Is that any better?
Mm-mm. 1 second. Yeah, we don't see at all the screen, I believe. At least, if I may ask as well to confirm in the chat that you are as a UC, or is there in general the issue?
Okay.
Can you able to share your screen now? I think yeah.
Yes.
Yeah.
Now we see. Now we see. So what is the fairness?
So what is fairness? Okay, and
apologies for your time, Tim. You can continue.
That's right. Okay. Fantastic. Okay, so sorry, you couldn't see the example before. So this is the text that I was showing off in terms of the movie review. This was the graph of the fairness relative to Human Development Index. And I was up to talking about target or reference bias. So here it's the individuals mentioned in the text rather than who wrote the text. That's the variable of interest. So you've got an excerpt here, a slightly confronting one relating to slavery, but taken from what's called the GAP data set relating to co-reference resolution. So we have the pronoun her underlined here. The question is, does her here refer to either Eliza Bryant or Polly Simmons? And the observation in the GAP data set was for male pronouns in English, the accuracy for co-reference resolution systems tended to be higher than for female pronouns. So that the fairness here is in terms of relative to how language is used and who is referred to in the language, you're observing disparities. Okay, so what are the sorts of protected attributes that people tend to look across when they're talking about fairness? It can be anything really. I guess common protected attributes are things like gender, often in the context of binary gender, race defined in some way. I know it's a problematic term, but defined often relative to different registers of language, say, or self-declared variables, age, sexuality, et cetera, et cetera. So just some examples of that. It might be hate speech and race, or review ratings and source variables, such as the age or the country of origin of the person who's written that particular review, and so on. Okay, so we know there's an issue. How do we go about resolving this issue? Well, a naive approach might be to say, well, surely if we don't tell our models anything about these predicted attributes, they're not going to be biased towards them because they don't exist as far as the training of the model is concerned. So I'm going to use as a running example this sort of toy illustration of, in our training data, we've got soft toy elephants and rhinoceroses. So that's going to be our main task variable. And we have attributes associated with those. So in this particular case, we know the color of these. That's our predicted attribute. So we've got access to that, but if we simply obfuscate that information in terms of training our model, surely we're not going to have any bias in the model that we learn. And the answer is it definitely does learn bias, and if anything, it tends to amplify the bias if you do this sort of simplistic fairness as blindness approach. So it's not a solution. Another sort of baseline sort of approach might be to say, well, what about if we expose the predicted attributes and explicitly balance our training data relative to them? The common issue that we have is minority demographics, which are underrepresented in our training data, tend to be those where we get these disparities. So in our example before for male versus female pronouns in English, a large part of the reason for that was the training corpora are very much biased towards Newswire, where you get a lot more mentions, unfortunately, of males than females, so that the training data bias seeps through in terms of the model performance. If we downsample the male references to make the number comparable to what we have for the female, does that solve the problem? And the answer is, well, it does in a way, depending on how much of a disparity you get in terms of the relative population sizes. It can mean you take a substantial hit to the amount of training data that you have access to, meaning that the accuracy is driven down because of that, the accuracy over the main task variable that you're interested in. So to some degree it helps in terms of fairness, but it tends to come at a substantial cost in terms of accuracy. So if you're interested in the trade-off between the two, it's not going to be ideal. So what can we do beyond that? So I'm going to focus primarily on adversarial learning approaches to try to mitigate bias. And the idea here is we want to strike a balance in terms of this trade-off, in terms of being as accurate as we can at predicting whatever our target variable is, our main task variable, and as bad as possible at being able to recover whatever the predicted attributes are for our particular data set from whatever representations we're generating for each of our instances. And so we're going to train our models such that we sort of get this good at target variable, bad at discriminating relative to these predicted attributes at training time, and at test time, we don't make any use of the predicted attributes. So coming back to our toy example, this would be the idea of we are using our predicted attributes at training time, the color as we're using here, such that for those training instances, if we try to predict, and equally at test time, if we try to predict for this thing that I've just labeled as an elephant, say, what is its color, we should be very as close as possible to a random or a majority class or whatever, depending on the data skew baseline in terms of our ability to be able to do that. So what does this look like? So formally speaking, the way that we train our models is we have our primary task objective, our first loss term, which is just simple cross entropy loss. And then a second loss term, which is the cross entropy over each of our predicted attributes, if we have multiple of them, maybe we only have one, and we want to do as badly as possible there. So we want to minimize the cross entropy for our primary task variable and maximize the cross entropy for each of our predicted attributes. And the way that we train our model is via this minimax configuration, a little bit like a GAN, but basically we're just iterating between training our main task classifier and training our adversarial discriminators, which are doing this prediction of our predicted attribute and iterating between the two over some number of epochs until we strike a balance. And we have this hyperparameter lambda to control the effect of the adversarial discriminators. So potentially one for each of our predicted attributes. So lambda I for each of our I equals 1 to n. Okay, so let's play around with this idea. So in the first instance, it'll just be a single discriminator per protected attribute that we're interested in. We'll look at this in a couple of different contexts, and this is work from a couple of years ago now when we first started playing around in this space. So the first task is a simple part of speech tagging. So we have a very standard at the time, a little bit outdated now, by LSTM, and we're going to pre-train a model over English web treebank data, fine-tune over a small subset of Trustpilot data. So Trustpilot is a website for reviewing companies or products, with the important property that reviewers on Trustpilot will sometimes divulge personal details. They will sometimes say, I am whatever, 35 years old and male. So we're using the self-declared demographic information when we have it from the individuals. So the two particular protected attributes we're interested in are age in terms of under 35 and over 45, based on previous work, and binary gender, male versus female. And so we're going to have a separate adversarial discriminator for each of those two protected attributes, which we're applying to our hidden representation, the concatenation of the respective LSTMs. Okay, so first, so our baseline model, we don't have any adversarial discriminators at all. The ADV, the second row there, we have these two adversarial discriminators. And what we observe first in the baseline case is we get this this delta, this disparity in terms of the accuracy of our part of speech tag outputs to some degree over the binary gender, and to a larger degree over the age. We tend to do better for older males, partly because the data is pre-trained over Wall Street Journal text, and that's the demographic of a 1980s journalist in the US. With the adversarial discrimination, we observe two things. So first, our deltas come down, so it's much fairer. The gap between the two values for each of our binary gender and our age is much less, but also overall our results go up. So we've kind of not just not sacrificed accuracy, but we've actually slightly increased accuracy, and the model being forced to generalize better through the addition of the adversarial discrimination. And perhaps more surprising, when we then took that trained model and applied it to completely out of register data, African-American vernacular English, across rap lyrics and subtitles from African-American media and tweets from the African-American community, we also get this big lift in terms of the accuracy. It's by no means perfect, but relative to the baseline, we're generalizing much better. We're much more robust over different demographics, even though we have no explicit training for this particular population. So very promising. And second set of results in terms of sentiment classification, 5-way in terms of 1 star to 5 stars, Trustpilot data again, simple CNN model, 3 protected attributes in this instance, so binary gender again, young versus old, I'm including myself as old, and location across 5 different countries. Here, rather than looking at it in terms of gap, the delta that we were before, we're going to look at it in terms of leakage. So if we train a separate classifier over the hidden representations that we're generating in our CNN to try to predict across these 3 different protected attributes what the value for a particular instance is, how accurately can we do that? So we want to be as close as possible to baseline here, which is our majority class baseline. And again, we find, if we have an adversarial discriminator for age, it's much harder to do it for age. If we do it for all of them, the overall results are largely unchanged. In fact, they come up ever so slightly, but I wouldn't read too much into that. But our leakage goes down a lot. We're differentiating in terms of the representations. We're learning a lot worse than we were before. So all sort of very encouraging to this point. And this is where we sort of have the buts. So that was sort of 2018, and all worked well in that particular setting of those two specific tasks. When we tried to apply this elsewhere, what we tend to observe is a couple of different things. So the first thing is training instability. So sometimes trains very well, converges very quickly. Our loss drops very rapidly, great. And sometimes loss doesn't drop at all, fluctuates, just doesn't converge. So they tend to be very finicky models. And the reason for that is we have highly non-convex decision spaces that we're operating in. And sometimes we sort of strike it lucky through whatever artifacts of the data, and sometimes we don't. And in terms of the generalizability of the method, obviously this isn't a particularly good thing to have. So subsequent work then, in terms of potential engineering fixes to this issue, looked at things like, well, we can obviously add more capacity to our adversarial discriminators, as in raw number of parameters. We can upweight the adversarial discriminators in terms of these lambda I values across our different protected attributes that we were talking about before. Or we can ensemble adversarial discriminators. So instead of having one per protected attribute, we can actually have multiple per protected attribute. With the classic ensembling expected result that should do better than just one. And what the authors Elazar and Goldberg observed in this work was they help, but again, it's a bit inconsistent. There's sort of no one panacea, one method which sort of just works across a range of different settings. It very much varies depending on the data. And one issue that you have with the ensembling approach, so the ensembling approach was possibly the pick of those, but as I say, it was a little bit inconsistent, was there's no constraint to ensure that the different adversaries, the discriminators, are complementing one another. You're leaving it up to randomness. So how can we fix that? By adding explicit constraints such that discriminators are learning as orthogonal as possible representations. They're not just all learning slight variants of the same thing or rotated versions of the same thing, which are going to be functionally equivalent to one another. So just to confirm, rather than having a single discriminator, we've got multiple discriminators per protected attribute with this orthogonality constraint between them. What that looks like is we do the pairwise, as in each discriminator versus each other discriminator, squared Frobenius norm between them. And we're going to sum that up across all of the different pairs where we don't have identity. And earlier, Nurip's work had shown that one advantage in a different context to this style of orthogonality constraint was it encourages not just differentiation, but also avoids the possibility of just learning rotated versions of what is largely the same representation. Okay, so let's come back and play around with some different data sets using this idea of this orthogonality constraint, this diversified ensemble of discriminators for different protected attributes. So we're going to do sentiment classification again. It's a newer data set for Twitter data. The protected attribute here is going to be a binary race as a sort of slightly awkward proxy based on standard American English versus African American English. And we're going to, again, evaluate the trade-off accuracy versus gap in terms of either true positive rate gap or true negative rate gap, noting that this is a binary classification task, as well as leakage again over our hidden representations. So accuracy, obviously, higher is better. What we have in the blue is just a standard model without adversarial discrimination. In the red, we have an unconstrained set of 3 discriminators. In the green, we have this orthogonality constrained set of 3 discriminators versus TPR gap, TNR gap, and leakage, where the lower, the better. So ideally, we want our gap metrics to be 0 for it to be a truly fair method. And what we're observing is both the variance goes down. If you look at the error bars, the absolute values improve, accuracy goes up, gap comes down, leakage comes down, as we add in this orthogonal constraint. So it definitely seems to be effective. And I didn't include the results for the single discriminator, but always better than a single discriminator. So better, more stable. We don't have all of these, or certainly anywhere near as many issues in terms of difficulty of training these models. But yes, there is certainly a bit of an overhead because we now have multiple of these discriminators that we're having to train. The orthogonality constraint doesn't really add anything computationally in terms of the time to train our models. Okay, so then the last scenario I want to talk about is this assumption that we've had up until now that we always have access to our protected attributes. So for every instance, we know we have a full set of data in terms of our protected attributes. And for a lot of data sets, it's just not the case. So either some individuals have disclosed certain protected attributes, others haven't, or they're certain things we're allowed to ask of certain individuals, certain things we're not. So we can ask if someone is over a certain age and hence eligible for the pension, say, so that we know that they're above a certain age. But, and so implicitly, I guess we know if people are below a certain age, but we don't know what their age is below that age because it's not appropriate to ask if we're trying to offer legal assistance, say. So age above a threshold, we know, age below, we don't. So how can we train our models in this partially labeled in terms of our predicted attribute data setting? Well, when we think about it, we quickly pick up on the fact that because we have this iterative training of our models in terms of our base classifier versus our predicted attributes, it actually doesn't matter. It's perfectly compatible with the idea that the supervision, the actual labels that we're using for the base classifier versus the adversarial discriminator can be different. So the partial labeling actually doesn't matter. We can just use whatever labels we have access to on either side. We can also go further than that in observing that, in fact, it doesn't have to be the same instances that have those labels. We could actually have an external data set where we've got predicted attributes, use those to train our adversarial discriminators, and a data set with whatever the labels for our primary task of interest are, to superimpose predicted attributes in instances where we don't have anything at all. So let's step through those different scenarios. So we'll start out with in-domain setting, again doing sentiment analysis, this binary classification task as we did before. So we're going to be comparing in blue accuracy versus TPR gap. The TNR gap correlates fairly strongly with it, so I don't have the second gap there, excuse me. In the different lines, what we have is different proportions of labeled data in terms of the protected attribute. So on the right, in terms of our legend, the dot dash, we've got fully labeled data, and right to left, we come all the way down to 1% labeled data in terms of the solid line. And in terms of accuracy, what we observe is very little difference in terms of, as we adjust our lambda, this hyperparameter in terms of the adversarial discriminator, we similarly observe that exactly at what point relative to accuracy we minimize our gap will change. But in each case, we get down to roughly the same level in terms of gap of 0. So even with only 1% of the data labeled, we can get roughly the same accuracy. And on a second data set relating to hate speech detection, it wasn't quite as, well, similar sort of result, I guess. Here we actually go down below 1% to 0.1% of the data where we have protected attributes. And again, we're adjusting our lambda parameter here to produce this frontier. I'm just plotting something slightly different here. It's accuracy versus gap rather than having the separate lines, but similar sort of effect. So you know, at the same level of accuracy, you get largely the same gap, even with 0.1% of the data relative to 100% of the data. And it's only really when you come down to lower gap values, so if you sort of drew horizontal lines in terms of a fixed accuracy, what is the gap? It's only for sort of lower accuracy levels that you start to observe much differentiation there. So again, we can get away with very little label data in domain. What about this out of domain setting though? So just to confirm, the idea here is, you know, we've got labels in terms of elephants and rhinos, to use our toy example again, but in terms of our protected attributes, we don't have any elephants or rhinos at all. We have whatever odd assortment of soft toys. We don't even know what they are, say, in terms of the animal type. All we know is color. So we're mashing these two labeled sets together in terms of using the elephants and the rhinos to train our base classifier for our target variable versus our adversarial discriminators in terms of our protected attribute. And you know, there's no reason we can't do this. So the question is, empirically, how well does this work? So what we're doing here is, again, it's sentiment analysis, but using the protected attributes from one data set and sentiment labels from a different data set. So the blue points, we're doing it in domain. The red, the orange crosses, we're doing it out of domain in terms of we're sourcing protected attributes from a completely different domain, similar task, but a very different domain. So to confirm, we're doing hate speech detection. We're doing sentiment analysis, but we're getting our standard American English versus African American English predicted attributes from the hate speech data set. So in this case, a completely disconnected task. And so we definitely get a drop, you know, even compared to using 1% of the data in domain versus using all of the data that we have access to out of domain. And I mean, again, we sort of tend to get bigger disparities for lower gap levels. So you can sort of see this sort of fanning out effect as we go from left to right as the gap decreases down. So definitely, if you have access to in-domain, you should use it. But if not, you get something out of it. You certainly get some reduction in terms of bias in using out-of-domain data. And I don't sort of have the standard model without any debiasing at all, but that's lower again. Okay, so just to wrap up this part, so very small amounts of label data in terms of protected attributes go a very long way. We can either partially or completely decouple the training of our base classifier with our adversarial discriminators in terms of our adversarial training, you know, even going as far as having data sets which have different target variables and meshing the two together in terms of protected attributes versus our main task labels. Just by way of mention, that there's sort of, as I've talked all about adversarial learning in this particular talk, you know, recent work from a couple of different conferences, from EACL at the start of this year and ACL recently. You've got the references to the respective pieces of work in the slides, which you should get access to, I believe, and you've got GitHub links to the code associated with all of those papers. We've been doing a lot beyond just adversarial learning. You've got a bit of a dump of it here. It's anything from instance weighting to max margin methods to constrained learning to contrastive learning. So lots of different approaches, and it tends to depend on the specifics of the data set and things like the arity of the target variable, what methods work best, and how you're doing your evaluation of fairness as well. Okay, so let me just summarize. we talked about fairness and the importance of training our models to try to make them as fair as possible, to mitigate the bias as much as we can, with a specific focus on adversarial learning. And initially observed that, yes, it sort of seems to work very well, higher accuracy and fairer, but also that we had this issue with the stability in terms of training our models. We then introduced this idea of orthogonality across our ensemble of discriminators, and that helped out appreciably. And then we talked about this partial labeling possibility. And yeah, lots of more work to be done in this space, obviously, with lots more room for improvement. So far from a solved task. As I say, very differing results across different data sets and different data settings. So what we really need to work towards is a sort of recipe for, given peculiars of the data set, what is the best sort of method you should be playing around with. And let me just conclude by acknowledging my co-authors on this work, Yitong Li and Shudong Han, as two PhD students that I've been co-supervising with my wonderful colleague Trevor Cohen, and this work's been funded variously by the Australian Research